My name is Michael Cherry. I look forward to taking you through the semester itself. Just by way of background, I'm an engineer, have many years in industry working through to general manager and managing director level. So I guess what I can bring to the party throughout these mini lectures is the practical application of many of the concepts that you'll see us tease out during the course of the semester. As engineers, many of our tasks come as a consequence of a request from an external or internal client. So our own organization or an external client itself. So they're presenting with some form of engineering problem for us to solve. So when we do initiate the engineering project itself, the manner in which we address this task, this problem, is what we call the engineering method. Now, there are other variations on this methodology, also often referred to as the scientific method in broadest sense. Also, those that have any association with the quality movement will recognize some of the elements of the problem-solving cycle, or the plan, do, check, act, and its variations. So again, utilized by many, but in this particular instance, we're going to refer to it as the engineering method, which covers 5 broad areas: getting some clarity around the definition of the problem in the first instance, and what are the performance criteria, what's actually required. Then gather some data, knowledge as we call it, do some research. Secondly, as a consequence of that, generate some alternative solutions to the particular problem posed. So there's never just one way to solve the problem, there are often many. So identifying some alternative solutions. Then make some effort to evaluate those alternatives against the performance criteria that have been set. So what's the outcome that we're looking? What is it? What's the problem we're looking to solve? What are we looking to achieve? So make some assessment of the alternatives against that, and then run some experience, trial, if you like, monitor, review, and check the outcomes. And again, that's to ensure that we achieve the specification of the impacts that have been required, so the performance criteria that's actually been suggested or recommended. And then finally, communicate, recommend solutions to our clients. So each of those in the cycle represents what we call the engineering method, and is used throughout our careers. I mentioned before my long career in industry, and I still use it for every project I undertake today, with particular emphasis on the first part around defining the problem and the performance criteria in the first instance. I think how many problems have gone unsolved or been solved many times over, poorly that is, because we haven't had sufficient clarity around what the real problem is and what the desired performance criteria is. And I'm sure you can think of similar examples in your own career. Okay. This diagram represents the engineering method within the context of the overall project management. So when we talk about the project management, we're talking about the collection of processes, all of the processes used to manage a project from beginning to completion. And we're showing the engineering problem-solving method wrapped within that overall project management process. So again, the addition of the client need or the client brief, which speaks to the overall project management approach, but it also kicks off the project, the problem-solving exercise that we have to undertake as engineers. So client brief, undertaking the research, generate some alternatives, evaluate, decide, recommend, and then closing the loop. So similar to the previous slide, but really just want to introduce the engineering method to the overall project management approach as it relates to solving all of the problems from project initiation through to project completion. One of the important roles that we play as engineers is helping our client getting clarity around the problem and what the desired performance criteria or level of performance, what that actually is. Often they need assistance in that regard. So the systems thinking approach is very, very helpful in that regard, because it forces us to identify all of the elements of the problem itself. And it's speaking, as you see diagrammatically here, in terms of what's the boundary of the problem itself. Where does it start? Where does it end? What are the assumptions we're making about what actually happens within the constraints of the boundary itself. So what are the component elements that need to be addressed? Importantly, because nothing we do ever nothing we do in a vacuum. We need to understand what are the interactions between the components and the project itself. So really keen importance to get some clarity around where the project starts, where it finishes, what each of the elements are within that, or which of the components are within the project itself, and to what extent do they interact with one another. So having a strong understanding of that and being able to present that back to the client in a fashion that gives clarity around definition of the overall problem, as well as as a thorough understanding of current level of performance and what the expected level of performance is. So systems level thinking allows us to add real value to our customers, to our clients, be they internal or external, by getting clarity around the problem that needs to be solved, as well as any interactions that might come as a consequence of those elements working together. Again, I mentioned in one of the earlier slides, throughout my career, as I look back at some of the projects I've been involved with, lots of them successful, but sadly some of them not so successful. And often when we go through the review of the projects there afterwards, it often comes back to a lack of clarity around the problem definition and the desired performance criteria upfront. So we're solving problems, but not the right problem. So as a consequence within the business, and we've seen it many times ourselves throughout our career, with others solving the same problems over and over and over again, because we haven't got sufficient clarity around the length and breadth of the problem and what the true desired performance criteria is or are. In an earlier slide, I introduced the concept, which I'm sure is well known to you folks, of project management. That is the collection of all of the processes used to manage a project from start to finish. We didn't spend a lot of detail on it, but now let's just tease out some of the elements of the project management approach. So you'll see we have 8 points to speak to here. I'm not going to spend a lot of detail on it today because we'll be revisiting this throughout the course of the semester itself. So, one of the very important elements is that of scheduling. So getting some clarity around what tasks are required, how long each of them will take, and also how much time is actually available, because we have this trade-off issue of time that's actually required versus the time required to actually get the job done. So we use the likes of the path methodology, Gantt charts, and so forth as a means to schedule our projects. You'll see an example of that on the graphic in the bottom right-hand corner of today's slide. In terms of resources, again, it's understanding what are the overall resources required for the project. How much time have we got? How much budget or how much money have we got? What sort of equipment have we got at our disposal? And also the people involved. So all of those are absolutely vital to understand our ability to undertake the project against the defined schedule, as well as also to achieve the outcomes required for our client itself. So with the key one being the understanding of the people involved in terms of how many people do we require, what are their skills and abilities, how can they work well together in a team environment, and so forth. So a whole raft of resources required to ensure effective project management. Also introduce what we call the design file. So that really reflects all of the records of your own work, collection of all the relevant documentation. Also, as we work our way through projects and project management exercise, some reflection on the process itself. Because when we do come to do a review at the end of the project, we've got some data that we can draw from rather than trying to remember it all after the event. So again, it's important to have these presented in a thorough fashion. Some organizations do digitally, others do it manually and so forth. But again, having them presented professionally such that we can actually review them in an effective manner and draw upon them either for our clients or for our colleagues to make use of the material that's actually in the design file. Okay, Talking about, and I did talk to some extent a little about this in one of the earlier slides, one of the earlier dot points on scheduling, the issue of time accuracy trade-off. So if we have years and years to do a project, obviously we can put a little more attention to it and lots of resources to undertake that project versus something that might be, back of an envelope type exercise and so forth. And where along that continuum does our project actually sit? So understanding that we do have this trade-off that exists if our time is not unlimited and our resources are not unlimited. One way or the other, there's always some degree of compromise around the outcomes that are likely to be achieved. Every engineer is very keenly aware of the importance of risk management and undertaking risk assessments. When we talk about risk assessments, it's trying to get some clarity around the likelihood of an issue occurring, as well as the frequency of that. So when we define risk, for example, we talk about risk as being frequency times severity. So the likelihood of it happening, frequency, and severity is what are the consequences of that particular risk occurring. So again, we have to go through this risk assessment process, get some real clarity around the impacts, likelihoods, and consequences, and that the risk is the product of likelihood of both of those, frequency times severity. Moving on to reporting and documentation, where we pull a lot of our material together through delivery towards milestones and so forth, similar to the exercise around documentation itself, ensuring that that's presented in a thorough, professional manner and speaks to all of the issues identified at the project initiation stage and works towards the performance criteria actually identified. So to do that well, we need to develop our writing skills and ensure that we can write in a fashion that's not just understood by ourselves, as well as our colleagues, but ultimately our clients and the likes. We talked about earlier the need for, in the design file, to just time to reflect on some of the processes we've gone through. We've pulled that out in the improving practice subheading that you see there, ensuring that we have some reflective practice on doing, thinking about the work that we've undertaken and some of the improvements that we might apply the next time that opportunity presents itself. So again, it's if you like, we talk about the problem-solving engineering method. It's our own, if you like, problem-solving methodology, making sure that we actually continuously improve in actually that which we do. So we do that either both at an individual level as well as at the team level. So if we're working on a project with a team, take the opportunity to find out what the team learnings are as well. Now, the last one speaks to one of the very important requirements of Engineer Australia, and that is the whole area of professional development and capacity for lifelong learning. So again, it's all vitally important that as a reflective engineering practitioner, we're always learning and we're always improving. Okay, well, earlier in the mini lecture, we introduced the concept of the engineering method, kicking off the client brief or the client need, undertaking some research, generating alternatives, evaluating those alternatives, deciding on the most effective and efficient outcome, recommending, and then closing the loop. So the engineering method. We also talked to, without populating the outer loop, which is the project management loop, we've now spent some time on the 8 elements of the project management process, and we've highlighted those here on the slide now. So that of scheduling, resources, meetings, documentation, the time accuracy trade-off, issues associated with risk, some personal and team reflection, and ultimately reporting through to our client itself. So you can see within the context of the overall project manager approach how the engineering method applies. It's described here as one loop within the other, but as you already know, there are lots of loops within the overall project management approach. But this is just a descriptor, just to show how the engineering method, the problem-solving approach, the scientific method, if you wish, if you prefer, how we utilize that within the overall context of the project management approach. And as I say, throughout each element of the project management project itself, we will go through the loop, the engineering method approach many times. Okay, we've talked about the engineering method and its position or place within the overall project management approach. I want to now move on to some of the problem-solving tools that we can use, particularly as it relates to generating alternative solutions for problems and projects themselves. We, as engineers, we're sometimes, unfairly, but sometimes accused of perhaps being not so creative, being very left-brained, very logical, linear in our thinking, which, as I say, is unfair. But if it is a challenge for us, some of the approaches that you see on this slide, the 5 W's and the H, research, brainstorming, lateral thinking, synectics, and TRIZ, can help us generate, one, creative solutions, and two, solutions that are a little more, take us out of some of our linear thinking approach. So the first one, 5 W's and the H, that's particularly useful when we're looking to actually understand the problem itself. So at the very start, when we're actually looking to define the problem and the performance criteria that's required, using the 5 W's and the H, and these constitutes the questions around why, what, when, where, and who, and adding the H of how. So as we are briefed by our client and taking the assignment brief, project brief from our client itself, all very useful questions for us to understand why things are happening, what's happening, how do they happen, when do they happen, where do they happen, and who makes these things happen. So again, all about getting clarity around the problem and doing so within a systems thinking approach. I mentioned before the importance that we play, the important role we play as engineers in actually helping the client get clarity around their problem. Often, and it's an issue that the quality movement sees. Often, we solve symptoms and not problems. We need to know what the real problem is, so we actually solve that, so we can ensure the performance criteria of piece of engineering equipment or whatever the problem is that needs to be solved. So the first, the 5 W's and the H, as I say, really very useful from a problem definition standpoint. The next is the area of research. Again, with the digital revolution, the ability for us to collect and capture a great deal of information is mind-boggling in today's environment. When we talk about research, we talk about two levels. We talk about primary research, so research we undertake ourselves to collect data, information, knowledge, as well as secondary research. Often there's a lot of work being done in related fields that we can draw upon to help us guide us in our work. So the importance of research, both that which we undertake ourselves, primary, or drawing upon work that's already available either online or through other sources, books, libraries, and so forth, to get a thorough understanding of the project that we're faced with. The next 4 points, those of brainstorming, lateral thinking, synectics, and TRIZ, are really all examples of variations of brainstorming, creative thinking approaches. So we kick off with brainstorming. That speaks to the need to generate ideas around the problem without evaluation, without judgment, get as many ideas up there as we can to help us get some creative connections to come up with better solutions. It's a technique that does take some practice. Often our thinking is very much on a railway track. We are products of what has come before us, and our thinking process is often takes us in the same path. So the brainstorming process is vital, particularly especially as when it's done in a group, because we can actually work off one another. But the important point here again is not to criticize, not to evaluate, not to make judgments on the ideas, but to capture as many of them as we can, get them up on the screen, on the butcher's paper, or whatever form that you've got there and everyone can see, and actually start to make some of those connections, generate some more useful ideas. So that's brainstorming at its most basic. If we move along to the area of lateral thinking, that speaks to a lot of the work has been undertaken by Edward de Bono, lateral thinking, parallel thinking, thinking hats, and so forth. again, to generate creative solutions. So a little more structure around the brainstorming process. For example, the metaphor of the 6 hats speaks to the sorts of roles that we might undertake in the brainstorming exercise, or the 6 thinking hats approach, which the slide's on the following page, but it talks about putting on a particular hat and then at different stages of the problem solving process. I mentioned on the previous slide Edward de Bono's 6 hats of creative thinking. These tease out what is happening when we are wearing each of those hats. So, for example, if we have a new problem to be addressed, to be solved, we need to gather some information around that problem, we all put on the white hat. So that represents gathering information. So again, helping to keep us focused, help us. We're still brainstorming, but give it a pathway and allow those ideas to generate freely, without evaluation, without judgment. So again, getting the benefit of the freestyle brainstorming approach, but pushing it in a particular direction depending on the circumstance. So I say very early on the project, trying to gather some information around perhaps project definition, or where we might source information in relation to the project itself, wearing the white hat. And then we have the other 5 hats that we will use at different stages during the brainstorming process, depending on the information that we're looking to tease out. So you see there the red color, heart, feelings and emotions. Black, to do with judgment, caution, and evaluation. So often there's a devil's advocate in the room, and they'll often be always wearing the black hat. But we should also put that on ourselves. So even if we're not the devil's advocate in the room itself, important for us to understand what are the risks, what are the issues associated with it. Optimism, so yellow, sunny optimism, sunny disposition. So even if that's not our particular disposition or our particular modus operandi, again, put ourselves in a situation and then generate ideas in accordance with the yellow hat. Green, colour of life, obviously generating ideas, and then finally blue for sky, representing high above the situation itself. So again, different hats that we use depending on what we're trying to achieve at each step of the process itself, and from a creative thinking standpoint. When we're looking to assess the feasibility of our various engineering solutions, we need to do so both from an effectiveness and an efficiency standpoint. So it's not just the technical solution that's often important, it's within some contexts of use of overall resources. So we need to consider both effectiveness and efficiency of our solution itself. So one of the ways that we can do so is through some of the economic solutions that we detail here more broadly. Now, economic feasibility just speaks to a model often prepared as a spreadsheet to assess the economic viability of the project over the life of that particular project. And we measure that in a couple of ways, either as we call the net present value. If that number that we identify, the net present value of the particular project, is a positive number, so greater than 0, that is, we'll consider that to be, from an economic standpoint, adding value. And the internal rate of return is another measure which looks at the overall project cost and benefit and assesses the overall return rate. Internal rate of return is IRR, when we set the net present value to 0. So again, if the prevailing interest rate, say, for the use of our funds in any given day is, for the sake of the exercise, 5%, and the internal rate of return is a number less than that, for example, that particular project may not be the best use of our money in broad terms. I'm ignoring some of the other risks that we might use to determine when we will actually apply those funds. But if it's greater than that which we could achieve through investment elsewhere, then the internal rate of return could well justify a project that's worth undertaking. So NPV, net present value of the project, all brought back to today's dollars, acknowledging that there's a time value associated with money, and the assumption is net present value greater than 0 is something that could well be considered as a solution that's economically viable. And the internal rate of return is when we set the NPV to 0, what sort of rate of return does that actually generate? And we compare that against a standard. It doesn't have to be the 5% number I suggested. And depending on the industry, depending on the business you're in, you'll apply levels of risk and look for a rate of return greater than that again. So again, two different models undertaken very easily with spreadsheets to identify the net present value of a particular project, which takes into effect the time cost of money. And similarly, another way of looking at the same exercise is the internal rate of return when we set the net present value to 0. Another very useful tool is sensitivity analysis. So when we look at the major criteria associated with a particular project again, and we vary that, that will give us an understanding of how robust our solution is. So if we find that some of our assumptions are such that any minor changes in those assumptions can lead to wildly different outcomes, some of which may not be acceptable, that's the sensitivity analysis assists with that particular process itself. Detailed economic modelling, again, variations on economic feasibility we've talked about before, often undertaken on a spreadsheet basis and very easy to actually assess. And then finally, we can't ignore, obviously, the technical feasibility of the project itself, but we do need to take it into context of having to be an economic outcome as well as a technical one as well. So I will remember in my chemical engineering degree many moons ago, one of my lecturers talking about the best design for some particular heat exchanger. I can't remember the detail of it, but and he said we should build it out of gold. From a technical standpoint, it ticked all of the boxes, but certainly from an economic standpoint, failed on that first hurdle. So again, the importance of understanding that we have limited resources. So any solution that we come up with needs to be able to satisfy both technical objectives as well as economic objectives. Okay, well, you've already seen in your own organizations and your own careers the importance of getting economic solutions as well as technically feasible solutions, but we can't ignore the elements of risk. So risk from a safety and quality standpoint need to be assessed and assessed very thoroughly within the context of our overall project itself. So from a safety perspective, again, have we undertaken risk assessments to identify the level of risk from our solution? I mentioned before, I'm a chemical engineer, so throughout my chemical engineering career, undertook a lot of safety inspection work around hazard and operability studies, or we call them HAZOP studies and so forth, again, to identify the level of risk and do so in a coordinated, thorough approach. Often the products and the solutions that we look to design are subject to various standards, Australian standards, New Zealand standards, indeed international standards. So it's again understanding what the relevant standard is that applies and ensuring from a safety and overall risk perspective that our solution actually complies with relevant acceptable standards throughout the globe.